Hello everyone, my name is Roy Jafari and I would like to welcome you to another video and another course. This is the first video of the course that we're going to start together, and we're going to learn about deep learning with TensorFlow and Keras. Of course, these are two APIs that we're going to be using, and these are amazing APIs that have a lot of flexibility. However, the majority of the conversation we're going to have are going to be around the deep learning concepts and deep learning applications. So in this video, we're going to start with the most important fundamental concept and methods that deep learning uses, and that is gradient descent. In this video, we are not going to be using TensorFlow or Keras. We're just going to be using our bread and butter methods and modules such as pandas and numpy and matplotlib for some visualization. But in that, by using those tools, we're going to learn about what is gradient descent and how it is relevant to deep learning. All right, so that's going to be our goal in this video. All right, let's look at our codes. All right, so the two modules that we are using in this video are numpy and matplotlib, right? So that's the only thing we're going to be using, right? Like I said, even though this is a series of courses regarding deep learning with TensorFlow and Keras. In the first video, we're going to focus on the foundational methods of deep learning, which is gradient descent, right? So let me just set us up with the example that we're going to try and learn the gradient descent with, right? So imagine we have a system that when we give it an input, we do something to it, it gives us an output, right? So normally this system that we want to be able to understand and predict is not sort of like, we don't know the underlying relationship, and that's why we're trying to use deep learning to understand that, right? However, for the purpose of this video, we do know that underlying relationship, and that underlying relationship is basically a mathematical equation. And whenever we input a value here, or independent value attribute, let's say in this example, we get an output or dependent variable, right? So y is equal fx, like our function, right? So we do know it, but we're going to be using gradient descent to be able to find an important attribute of it, which is the optimum point, right? So this is the function, right? We call it the system, something that we don't know yet, and we're not supposed to know, but we do know because we want to learn about it. So this is our basically our function fx, right? And here if we wanted to find the minimum or the optimum point of this function, mathematically what we would do, we would be using the derivative of y or f(x) over x. And when we calculate that derivative, and when we equate the first order derivative equal to 0, it gives us the optimum point, right? And the optimum point, which is the minimum here, is 25. So if we put x is equal to 25, we know that our system is going to be at its minimum, right? So it's a mathematical way of going about this. However, let's say we don't know this and we don't know this formula. How about we just look at this as a black box and try to figure out what's the minimum point using gradient descent, using this method that is basically an optimizer. So let us keep setting us up with more tools to be able to understand this concept better. So first off, we're creating a function that basically is drawing our system to basically show us how our system looks like, right? So based on different value of x, right? So x lem, like from 0 to 50, we're basically getting the function gets a function as an input and calculate the y's based on that input function, right? And then basically plots it and shows the plot, right? So this is our function, and let's go ahead and draw our function. So this is the function, and basically from 0 to 50, this is the value we get if we put, let's say if we put the put x as 10, this is the value we get, and so on and so forth. And we can see here that when we are at 25, we're at the minimum. We calculated that mathematically, and we also see it visually, right? So now we are setting ourselves up in a great way to understand this. So the goal here is for us to, without having these mathematical help or visual help or computational help, to be able to calculate the minimum value using a methodical approach. Why would that be useful? That would be useful because we cannot always calculate. It's not computationally logical to calculate everything, every possible values to get the minimum or like find the optimal point, or it's not possible to find the mathematical derivative, right? So the real world systems, when we just get the output based on some input. We want to be able to connect these two by a method, and that's the gradient descent that we are learning. I mean, there are different methods. This is in this video we're focusing on the gradient descent, right? So let's create another function. On this function, the difference is from the previous function is that we create the whole, sort of like show the whole function from 0 to 50, but at the same time we also show one point that on this figure, like we want to see where that point would end up, right? So this is that function. Let's say we have that, so we say our x equal 10 is here, right? So and that's its value. If we change this to, let's say, 25, we go right to our optimum value, or if we move to 49, we get to over there, right? Let's go back to 10. So that's another development on this function. So we want to continue with that. Now here, this point, right? Based on this point, we can calculate a local slope based on where this point is, right? We can calculate that local slope and the tangent line with a very simple calculation, right? We can think of an epsilon, a very, very small number, right? And we say, okay, let me find what is the value of my function, my system, in p minus epsilon, right? So x1 p minus epsilon and p plus epsilon. A little bit before and a little bit after that point. And we find that the slope of that line, right? We find the slope of that line based on these 2 points, right? So that's what this function does, right? x1 is p plus epsilon, x2 is p minus epsilon, and we calculate the y1 and y2 based on the function. And now we can output this line as a lambda function, right? As a function. And we can also output the slope and our intercept of that line that passes from here, right? So this is our tangent line, or the slope line of this local point, right? So once we run this and we, let's say, calculate the slope of our system in that point, in point 10, this is what we get. So this is, I need to change this to this. All right, so we say our slope is negative 60. The intercept of that line is this, and this is the function that would be able to calculate the value, if we give it x, the value on that line, right? So this negative 60 should be equal to whatever we put in this formula, 4x minus 100, right? So x was 10, 4 multiplied 10 is 40, minus 100 is negative 60, right? So that's basically our approximation of what is the slope of that line, this curve in that point. That's basically what derivative is, right? So now that we are extracting this using this simple calculation, we can draw that line here as well, right? So this is another function draw system point with tangent line. We are also adding the tangent line here, and what we do here is that at some point we call our function extract tangent line, which is basically a function. It gives us a function that once we basically based on x, it gives us the value of that line, right? And we add that to our visualization, right? So that's going to be helpful for us to understand our gradient descent method, right? So that's that line, right? Based on using that simple calculation, we're able to calculate this tangent line, right? So we can like change this into 15, for instance, and it changes there, and you can see the tangent line. Or like we can change it to 5, right? The tangent line moves with that. We can change it to 40. Do you see like we've got that tangent line? So here's the whole thing right now, right? So this is the idea of gradient descent. Let me go back to 10 here. So the gradient descent idea is that if we are capable of calculating the slope of a differentiable system or a function, we can find its a direction towards which we can improve our goal, or improve the value of our function, right? So the goal here is to find what is the x that makes our system to be minimum. Since the slope here is negative, right, we can say if we were to add value to our x, which is 10, by a little bit, we are going to move in the direction of improving, which is decreasing our function, right? So our goal here is to find a minimum, right? So if our slope is negative, which is here is negative 60, right, we can add to this x as 10 to move towards making this smaller, making the value of y smaller. And if our slope is positive, let's say, let's go to 40, right? So our slope is going to be positive 60 now. We know by decreasing the x from 40, because of this, the value of the slope, we can calculate, we can move towards the optimal, or move towards our minimum value. If you are looking for a maximum value, then if our slope was positive, then we wanted to add, and if our slope was negative, we wanted to deduct. So that's basically based on if it's minimum or maximization, right? So here's the whole method, right? So we basically, based on where we are, based on the slope and the value of that slope and the sign, we choose to move the x value a little bit. And here's another function that calculates the proposed move, right? It outputs the proposed move and also draw the function, right? So it calculates the move and return it. And the move is calculated by the slope multiplied by a small number, which is called a learning rate, right? So here the learning rate is 0.15. This is something that if you are going to use gradient descent in actual production in a methodical way, you would have to tune this learning rate. But here we've set this learning rate at 0.15, right? So basically this function is going to give us a proposed move and also draw the point we are right now and the slope and the tangent line, right? So here at this point, x is 3, our slope is negative 88, and it's proposing that we move 13.20, right? So by moving 13.20, we change this to 16.20, and then we can run this again, right? So we moved closer to the optimum value, and it says you're at 16.20 based on the slope being negative 35, and let's move 5.28, right? So we move 5.28, right? And we get closer to the optimum. You can see as we get closer to the optimum, because of the learning rate, and because of the fact that the slope changes, now the slope is like not as high. It used to be 80, now it's 14. Our speed moving towards the optimum point slows down, right? So that's basically the whole thing here, right? We keep moving towards the direction of the slope and the tangent, which is also called gradient, right? So we move towards the gradient based on the signal we get from the gradient. We move towards the optimum point that we're interested in, right? So let's put this in an algorithmic way, right? So my first X candidate is 3, and I want to do this thing, find the proposed move and add to my candidate 20 times, and also draw where I am for us to understand, right? So I can just do this, and we can see that within a few iterations, I move closer and closer to the optimum value, right? So I got to the 25 after 10 iterations. Pay attention. If you pay attention to what we have done here, I mean, we are seeing this move because we set this up as a way to understand gradient descent. However, if we really didn't know and we didn't have access to the fact that our system is using this function, right? With gradient descent, we can actually find what is the minimum, what is X that makes this function, what makes this system to be minimum. And that's the whole thing, right? In the real world, there are a lot of times that we don't know where the minimum is going to be, and we don't have the computational capacity to try everything. Therefore, we end up using a system like this, a method like this, to find that minimum value like this, right? So the beauty of it is that now that we have sort of created a gradient descent method with some visualization, we can try this with almost any new function, right? So let's say our function is this one this time, and now we can calculate that minimum value, which visually we know is 20, by gradient descenting, right? So we get to 20 with this gradient descent method again, right? So in summary, in this video, we learn conceptually what is gradient descent, which is basically being able to find the gradient, the point gradient or point slope based on the value that we can try, right? And use that as an indication as where should we move towards, and move our value, move our input variables, move our decision variables towards a point that we get to a gradient that is 0 or close to 0. And if we, let's say we move from negative, and our gradient becomes positive, we move back, right? We may have to do a little bit of rocking in the end, and then we get to our optimum value. All right, so this was gradient descent. Stay tuned. We're going to start using actually TensorFlow and Keras in the upcoming videos. All right, until next time.